Okay. Okay, so calculus 2. So calculus 2 is primarily in the beginning it is primarily about the integral that the introduction to which you already saw in calculus at the end of calculus 1, and so we'll just keep going so that we get it at least as deep as we got with the derivative. Okay, so now we're doing the same with the integral. All the applications will appear, and then secondly is the series. Okay, so depending on what kind of calculus 2 you calculus 1 you had, it might you might have seen sequences, or maybe you haven't. But so it's based primarily on sequences, and I don't have to explain to you the need for the integral. Well, unless what is the use for the integral? What? Okay, anti-differentiation. So indeed, so it's the differentiation answers the question, and this is the. Well, hold on a second. So derivative is, if the differentiation is the question, derivative is the answer, and this is vice versa. Okay. So differentiation, anti-differentiation, based on the fundamental theorem of calculus, it tells you that the integral and differentiation cancel each other. But more specifically, you go to interpret your function as a location and your derivative as velocity. Then if you want to have some kind of to hold on to an idea about the integral, it is about how to find your location from the velocity. Okay, so this is actually I have this over here picture, as you can see. So a picture of calculus in one picture. Okay, so let's see, finding the going from right to left. We know what. Hold on a second. Yeah, we want to go how fast. We want to know how fast we're moving, even though our speedometer is broken. Okay, so how do you do it? You just record your location as often as you can, and then carry out this little computation of calculus to find the velocity. You will end up with the average velocity. So what is the average velocity? Well, no, actually no. Derivative is the instantaneous velocity, the average velocity.
What's the slope?
It is the slope of.
The function.
It is the slope of the secant line. The point I want to make that this is the average rate of change over this interval AB. Okay, so if your function represents location, that average rate of change becomes average velocity. Okay, so in that is the idea that I'm trying to put forward here, is that even though the speedometer is broken, you can find your velocity through very simple computation, which, when taken to the next level through calculus, will give you instantaneous velocity. So certainly, when all you have is this, you have just a bunch of numbers. You put them, you know, subtract and divide. So location minus location, that's what the slope is, right? Current location minus last location divided by time passed. That's the average velocity. If you want the instantaneous velocity, what do? You take the limit. So limit with time passed going towards 0, and the end result is either instantaneous velocity or the derivative. So the derivative of the location. So location is a function of time, and then velocity is a function of time. What's the relation between them? One is the derivative of the other. And then if you want to go backwards, then the one is the antiderivative of the other. Okay. So y equal f of x. Okay, so back to this example. Calculus 1 is then the first line from a function to its derivative, and the calculus 2 is primarily, or at least that part, the big part of it is how to get backwards, how to get from your knowing the velocity. So this is the next line over here. So you know the speed. Speedometer is working, but you want to know where you are. How do you do it? You pretty much integrate. Even though you probably do. Well, so what do you do with it? So you have your speedometer and a watch. How do you find your location? That's right, and you do it as many times as necessary. So the shorter intervals you take, the more times you repeat that computation, the more accurate will be your evaluation of your location. So once again. So location, or well, better to describe it is to say, and to call it the displacement. So it will be your velocity. Where does it come from? You just looked at your speedometer once in a while times time interval. Okay, and then that's during one period of time when you sort of assume that the velocity, that short moment of time during which you looked at your speedometer, that number tells you everything you need to know. You don't assume that there is a lot of variation of the velocity. Then this is how far you went in during that period of time, and then you sum it. So add these over several intervals. Okay? And the name of this is of the sum. What's the name of the sum? The Riemann sum. So this is the Riemann sum. We'll review that again in a minute. And then the final step is, once again, just like with the derivative. So this is what we did, and now we're doing pretty much the same thing, but computation is quite a bit different, naturally. But we still take the limit. We certainly start with algebra. So algebra here is what? Multiplication and addition, while the other one is it was subtraction and division, right? So the average rate of change, your average velocity, what do you subtract and then you divide, okay, and then you take the limit, okay. So these are the steps. So subtraction, division, and limit. Okay. Similar here, except we have what? We have multiplication, we have addition, and then still limit. And the limit of the Riemann sums is the Riemann integral. We can certainly carry this out every time, this plan, and we will, even though there will be shortcuts, and the finding integral sometimes can be done with nothing but a table, and that's how you using the fundamental theorem of calculus. But ultimately, we will have to go to the definition many times. The definition of the integral is this. So that's the definition. We'll see later why we cannot jump to the integral itself, and we have to retrace our steps all the way from the beginning. So computing in addition to areas, computing areas under the graph. That's what you did in calculus 1. Okay, and then computing surface areas, computing volumes, and computing all kind of things that are not on the list. Okay, so that's the overview of calculus 1 and 2, integral calculus, differential calculus followed by integral calculus. Okay, so that's a major part of calculus 2. The second, as I mentioned, it is series and sequences, with the goal of which is to approximate functions. Okay, so you got a little bit of that in calculus 1. Remember linearizations or linear approximations. Remember linear approximations from calculus 1? What's a linear approximation? So suppose this is my graph, and I have a point over here. Pick a point here. What's the linear approximation? There's a linear, and it is approximation. So there's a function, and we approximate it with what? With another function. The function that is linear. What is a linear function? What does it look like?
Straight line.
It is a straight line. So, but there are look at it. There are many straight lines. Which one is the right one? The tangent line. The tangent line is in fact the linear approximation. Okay, so in fact the full name is the best linear approximation because there are all of these straight lines I drew there count as linear approximation, but one of them is the very perfect one. It is the one that has the slope equal to the derivative, and that is the tangent line. Okay, so where do we go beyond this? There are approximations that are quadratic. So linear, quadratic, cubic, and so on. These are the approximation of all the functions that are better than linear. So you can imagine that this one has certain concavity to it, right? So the linear approximation loses that information about it. But if you try to think of a parabola, maybe it might look better like this. Okay, so that's a quadratic approximation. Okay, so quadratic, there are still gaps there. As you move away from that point, there will be still gaps, whether it is linear or quadratic approximation. But look at it, it's better. It is a better approximation. So that's the chapter about series, and the third item on the list is parametric curves. This is an introduction into multidimensional calculus. So it really, we are limiting ourselves to, if we study motion, we don't really want to limit ourselves to something like that. So you look at it, it all works out quite nicely, but we are driving on a straight line. So this interpretation, how to find the average location from velocity from location, works out fine, but when you're driving on a straight line, you have one number in your speedometer. If you are moving like this, well, so that's out. So if your road makes a turn, you cannot just use calculus 1 for studying these things. And so that's what parametric curves are. They give you motion on the plane, not on the straight line, on the plane, in three-dimensional space. And so all kind of the physical applications are then, inevitably require parametric curves rather than calculus 1 approach. So, and that takes you, they take you to eventually calculus 3. Okay. So, any questions so far? Okay, so these are the 3 topics. We'll go in that order, just as the book does. And so we'll start with the integral. So we'll start with a review. So this wasn't like an overview, but I think we do need to take a look at the definition of the integral, or Riemann integral, from the Riemann sum, and then look at some applications. Okay, so the Riemann integral. So the purpose, you certainly remember that the Riemann integral is ultimately of a function is about the area under the graph. But let's not forget that approximations are not just necessary to define it, like the way I just did, but they have independent value. Okay, so we define them. Here are the Riemann sums. Okay, so you have the same thing, but we need to understand before we get to compute anything, we have to understand what the meaning of the area is, and the only way to do it is to approximate, and just the way it was done early on by ancient Greeks, except they approximated they approximate the area of a circle, for example. And then for them it was inevitable. They did not have functions. They did not have the Cartesian system. So that's why the approximations were with anything triangular. So like, for example, a square inside of a circle, and then you insert a pentagon, a hexagon, and so on, and then it gets closer and closer to the area in question. And that's how they approximated. They came up with the formula pi r squared. Okay. And then you do the same on the outside. Well, so we are in that place, and so to approximate what's above, what do? We divide the domain into small intervals. The interval is AB is divided into n intervals. Okay, so the idea is then to take this region and slice it into thin, hopefully, regions that are the top of which is almost straight. Okay, so that curve, our original curve y equal f of x, certainly goes up and down, but if you narrow it down, you can see how this piece, for example, is almost horizontal. All of them are not have a lot of change. So that's the idea of approximation. So we're going to replace each of those still curved regions with rectangles. Okay, so that's the Riemann sum. Okay, so this is how A is equal to x naught less than the x1, xn equal to b. So these are the n intervals. So as you can see, n plus 1 points with n intervals. This here I have n equal to 4, just as an example. Okay, and then what's the next step? So we have this, and what I have is we approximate the area under the graph with the sum of the areas of those rectangles. How do we approximate the area of each rectangle? So how do we do it? I mean, it's still not a rectangle really, but it almost is. So how do we approximate it? Yeah.
Would you find the total area and divide it by n?
No. No, that's backward. Then if you already know it, then why you go backwards and divide it into pieces? So we don't know what the area is. We don't even know what it means to have an area. So that's why we have to start it with approximation, division into smaller pieces. Approximate each of the smaller pieces with an actual rectangle. So this rectangle looks like this. Not a rectangle; it's curved. We approximate it with this, some rectangle which actually has a top, straight horizontal top. So this is the approximation. Curve things on left and an actual rectangle on right. Okay, so we approximating this with that. So where does this rectangle come from? The second one. The first one is just a slice. What's the second one?
Approximation.
Yeah, so how?
I find the area of the rectangle.
Yeah, okay, so but we don't have the second rectangle yet. Where does it come from?
Oh, it comes from the second point on the end intervals.
Well, the red one, the red line here is our graph. Okay, so the only thing so far that we know is the base. So this is known. The base of the rectangle is known. It is the height that is unclear. So how do we find the height? Say it again. Yeah, two of them. Yeah, so what do we do with them?
You take the distance between them?
No, that will give you the base, yes. So known, this is the base. Base is equal to, say, x k minus xk minus 1. Okay, so this is the base. Okay, so we do know it because our area we're looking at, as well as its approximation, they have the exact same base. It's the height of the new rectangle that we have to figure out. The first one is not really a rectangle because it has a curved top. So what is the height? What should we choose to be the height of the new rectangle to approximate?
Would you take the y value of the midpoint where the graph, the section is being taken like the midpoint?
Right, in midpoint, or what are their options? Left and right hand, or any other point is actually equally eligible to give us the height. So the height is f of c sub k, where c sub k is a point in this interval. It could be, once again, as we just discovered, left, right points, midpoint, and well, that's it so far. The specifying that point serves only one purpose, and that is to make it specific, so that we would have the same pattern for every rectangle. So, for example, we have n rectangles, right? And we have n intervals, so we have to find the height for each of these rectangles, and we have to do it. It's easy to do it if we just pick the same point for all of them. For example, every interval pick the left. So left hand, ck is equal to xk. Okay, so and then on and on. Right point will be the other one. I'm sorry, minus 1. So this left. ck is equal to xk, right? And then the midpoint, how do I write midpoint? Xk is on the right, xk minus 1 on the left. What's the middle? What? The sum divided by 2, xk minus 1 plus xk over 2. It's not really that important, even though if you do carry out this computation, that's exactly, it is important because that's what makes it specific. At this point, what I'm saying here is any point will do. Any point I pick, let me make that picture. So I have my curve like this. I'm zooming in on my curve like this. And then what is the height? Well, I pick anywhere I choose. I could pick ck over here, a simple point, it's what's called, because literally our function is being sampled. Just like we sampled, remember we sampled our velocity. Looking at the speedometer samples the velocity. So one value, even though changing, it might have infinitely many values changing continuously. You look at it, take one look and write it down. That's sampling. So this is where CK is when I choose to make that sample. And then that unknown, the red curve is unknown, but I find at least one point on it, and then I choose this to be the height of my rectangle. Okay, so this is what I do. Okay, so then this is my rectangle. Not much of an approximation, but that's the idea, and you can see how the approximation will get better and better if the base is narrow. As it's narrowing down, the approximation will be better and better because the parts that are questionable, this part is questionable, and that one, they will be getting smaller and smaller. Okay, so the computations then carry out in this fashion. I don't want to stick with the with formulas, and since we are doing this, let's carry out one computation in this manner. And the computation that I like to carry out approximate the area of a circle. So what ancient Greeks did by hand, we can do with Excel. So that's what I want to do now. Okay, Excel. Okay, so once again, the problem is, let's use the idea of Riemann sums to approximate the area of a circle. So have you done a computation of the area of the circle in Calculus 1? Well, this you know what the idea is. It is the same picture as I have it over here. That's what we're dealing with, like that. Except now I'm making it specific. So I want this function to be specific rather than general, and so that the number will be at the end of the day. There will be an actual number at the end of the, because computers are not, they don't understand this. They have to be given very specific instructions. So the function will be specific. Then the subdivision of those intervals will be also specific. That's not hard. And then each time we're going to pick either left end or right end or midpoint. Once again, a specific decision made by us, so that computer would know what to do. Okay, so all right. So I'm going to start with this. By the way, is how many of your projects will go on. Okay. Okay. Okay, I don't think it's working. Let me try to close this maybe. Everything is messed up here.
Yeah, it's touching right now.
I think I'm back to normal, right?
Yeah.
Yeah, okay, great. So, yeah, I might need help sometimes. So, thanks. Okay, so what I'm going to do is I'm going to plot the graph of this function that represents the circle, and then I'll find the area under the graph. Okay, in what manner? In the manner of the Riemann sum. I actually didn't get to the Riemann sum, so let me write the Riemann sum. Sorry about that. So then the total area is the sum of f of ck times delta xk, which is this one. Okay, k from 1 to n. So that's the Riemann sum. The Riemann sum, so once again, there are many ways to choose the Riemann sum, and you can have many different points chosen, and varies, and then the choice of points, sample points within each of the intervals also varies. So you have to specify that in order to carry out the computation. So okay, so I'm going to plot y equal f of x. What is the, well, let me start. I think I'm in this place again. How did I fix it last time? Somebody help me. Who helped me last time?
I just know what mode it's in. I don't know how to get it out. Up at the top is that
I can't see the person. Who's? Oh, okay. I'm sorry.
top left, is that under?
Top left?
Yeah. I can't
This?
see very well.
It's no, just save. What?
The right
What is that? Oh, interesting. Okay, so I switch to mouse.
Yep.
Okay. No, I still have this stupid thing. Maybe I switch to touch. No. What? How did I? Just a minute ago, I fixed it without knowing it. Yeah, I clicked here, and then it switches back. Okay, I'll have to sort this out. So anyway, okay. So I'll put x's here, and I'll put y's there. Okay, so x's will start with. Let's do circle radius 1. So I'm gonna start with the values of x1 between what? What are the values of x? Negative and positive 1. So I start with negative 1 here, and then I will be adding, say, how about, so I put h over here, the unit step, it's delta x pretty much, and I'll put here 0.1, just because I like it. Okay, this one doesn't work. Okay, okay, so plus is equal to this, plus A1, A2. Oh, okay. Okay, so see that these are the x values. Long. Everything is done in a terrible manner. Okay, let me fix the settings. Options, formulas, no formulas. Yeah, R1C1's reference style. Okay. Okay, so as you can see, numbers on the column and rows as well. Okay, so this one I'm adding R2C. Okay. No. Number. Okay, no. What's wrong with this thing? R2C, R1C2, R1C2. Okay. What the hell? R1C2. Damn it, goes all over. Okay, finally. Okay, so, okay, they exactly are running from negative 1 to 1. So these are the x values. Okay, give me the y values. No, the y values, there have to be a function here. So what's the function for the circle?
X squared plus y squared equals your radius.
Right,
So
which is 1. So x squared plus y squared is equal to 1, but we have to explicitly express y in terms of x. So what's the formula?
the square root of 1 minus x squared. Right?
That's right, yeah. Square root of 1 minus x, not x, but rather this value, squared. Okay, 0, down, okay. Okay, so x's and y's, if you're not sure, let me plot it for you. So, okay, this is a circle. Oh, we plotted only 20 points, but since we're doing approximation, that's okay. So we're plotting 20 points. Excel connected them by a curve, so that curve is not a part of our data. The data, only these 20 or 21 points is all we know. Okay, so it's been plotted. Okay, now, but we're not interested in this picture. We're interested in the area. So what do we do with it? What happened again? Okay, so in each row, we will have the area of the rectangle. Okay, so, well, actually, let me do rectangles for you. So that this is the curve, but there's another way to do it. and we could insert simply the bars. Well, not this one, maybe this one. Okay. So this is the same picture pretty much. This is the same graph, but now it is clear what we're talking about. We're talking about areas of the bars. And these the bars, the heights of the bars are already okay. The only thing remains is the width. The width, just visualization is with the width where that is too narrow. But otherwise, you can see what we're after. We are after finding the area, the total area of these rectangles. Okay. So by the way, the number of points that we have is how many points do we have? So so starting with the 0th point, and then we add 1 at a time. So it is equal to this plus 1. Okay, and so we have, as you can see, we have 21 points. And how many rectangles? 20 rectangles. 21 points, 20 rectangles. So we'll now, in each row, we'll find the area of that rectangle. Okay? So, I mean, there are 21 rows, actually. So I'm going to start over here, not in the, at the 0, 0 level. I'm talking about this rectangle. And I'm going to be plotting it. I'm going to be computing it. So, okay, so what's the area? Width times the height. What's the width? 0.1, right? It comes from h over there. It is simply, or I could subtract the 2 consecutive values. I could just subtract this minus that. Okay, and multiply by the height, which is the y. That's right. So this is the y. Okay, so take another look at the formula. I think is it large enough? I think. So once again, look at the formula, what we're looking at here. So the first, in parentheses, I have the difference of 2 consecutive values of x, which simply gives me delta x, the width of the rectangle. It is multiplied by the value of y, which is the height, what we just talked about. The height is found by sampling our function. Our function is given by that formula which we just entered in the column y, but we are just taking one value, and we ignore that 0 over there. Okay, so okay, are we doing left hand, right hand, or midpoint Riemann sum? Which one is it?
Left.
No, it's actually right. So as you can see, we are looking at the first 2 rows, which is the first interval from 0 to 0.1, and which value do we pick? We don't pick from the first row, we pick from the second row, which makes it the right end. Okay. Okay, so enter, and then I spread it out. Okay, so these are the areas of rectangles. So I don't know, areas, and then what remains is to add them together. So these 20 numbers will have to be added together. So I'll put it here somewhere, equal to the sum of these. Okay. What should the number be roughly?
3.14.
Almost. We are getting only half of the circle. So half of that. Right? So the full circle is pi r squared. R is equal to 1, so it will be simply pi, 3.14 roughly. And then if we are doing only half of it, right, the only half of upper half of the circle, it will be 1.5 something. Okay. Okay. So that's our approximation of the area of the circle. It is let's compare to the exact value. So this is the total area. In other words, well, let me just say this is Riemann sum. Riemann sum is equal to that. Okay, I'll compare it to the actual exact area. Exact here. So as I said, it should be pi over 2. So equal to pi over 2, 1.57. Okay, so that's the quality of our approximation is visible here. So the actual number determined by integration, that's still to be learned how to do it, as a matter of fact. And we did it with 21 points, n is equal to 20, and therefore 20 rectangles, and the area is 1.55, as approximates the actual value. Okay, so well, that's how it works. So it's all totally legitimate of how you can compute the areas without actual integration. So as you can see, the only thing that I used from calculus was the formula for the circle. I did not use, I didn't do differentiation, integration, or anything like that. I did no substitution. I didn't do anti-differentiation. I didn't use the tables, anything like that. Because it's an approximation, and we can, it doesn't matter what that function is, how complicated it is, how complicated that curve might be. This is the curve, by the way, over here. Remember that formula. Hold on, this one. Okay, as you can see, that was pretty simple, but it doesn't matter how complex it is when the computation is nothing but, what is it, subtraction and multiplication and addition, that's all. So it's purely algebraic computation. Certainly, Excel is unable to integrate, not in the literal sense, the way you did in Calculus 1, but it can approximate anything you want, and the accuracy can be also made as large as you like. So I have 20 rows, I'll make 50 rows. And the accuracy will increase proportionally. Okay, so we'll just continue this next time. So think about the syllabus if you have any questions.